Hello everyone. My name is Vladimir Šimović. I'm a lecturer at the Department of Electrical Engineering at the Zagreb University of Applied Sciences in Croatia. Today, I will be presenting you a paper that I've done with two of my colleagues, Luka Lažita and Ivor Marković, from the same institution and the same department. The name of the paper, as you can see on the slide, is Infinite Impulse Response Filters Designed for Comparison and Minimum Order Design Exploration using Matlab. So let's get on to it. The first step of this presentation would be a small, short introduction to filters, especially low-pass filters. Then I'm going to present to you the IIR digital filters, or that's the abbreviation for the infinite impulse response digital filters. And I'm going to present to you the four types that we're going to take a look at: the Butterworth filter, the Chebyshev type 1 filter, and Chebyshev type 2 filter, and the elliptic filter. And then we're going to talk and define the term minimum order design. When we're done with that, we're going to compare the filters and talk about what we've done and how we reached the conclusion that we're going to cover at the end of this presentation. After that, we're going to have an open space for some Q&A. So, first, a short introduction for the people who are not maybe that much into this topic. The meaning of the term filter would be a system that changes the frequency content of a signal and completely removes unwanted frequency components from the said signal. The most important division of electronic filters would be according to the type of signal they filter. So we divide them into analog and digital filters. Of course, the typical question would be which ones are better. So we have a small and short comparison on the slide, where we can see that analog filters are cheaper, faster, and they have a very large dynamic range of amplitude and frequency. In parallel, digital filters have the ability to implement complex signal processing algorithms that are difficult to apply into analog technology. It's easier to program something than to build it physically. That would we have to done for analog filters. Also, digital filters have a better effect in relations to the price, and they don't suffer from manufacturing errors and do not age. When talking about filters, we are of course talking about realistic filters, and they can only have frequency responses that approximate ideal characteristic, as shown in the figure. So, unlike an ideal filter, the realistic filter consists of three segments, which are passband, transition band, and stopband. In the passband, as seen on the picture, the gain is relatively high, so signals can pass through. In the transition band, the filter gain gradually changes from 1 to 0. And finally, the third segment is considered to have the gain relatively small, so signals can't pass through. Another important division of electronic filters would be depending on the frequency band that either transmits or attenuates the signal. So, because of it, we divide them in low-pass filters, high-pass filters, band-pass filters, and band-stop filters. According to the above, the frequency responses can then be approximated in several ways. We examine the operation of a typical IIR low-pass digital filter to appreciate the essential differences between several standard approximations. Digital filters can also be divided depending on the response to impulse excitation. In that way, we divide them into infinite impulse response filters, that has the shorthand IIR, that's sometimes a bit hard to pronounce because of the two I's in succession, and also finite impulse response filters, FIR filters. A major advantage of the IIR filter over the FIR filter is the ability to approximate the desired shape of the amplitude characteristic well with a relatively low order filter, and that's a desirable quality. However, the IIR filter, unlike the FIR filter, cannot have a completely linear phase characteristic, which may be a disadvantage in certain applications. Since the ideal low-pass filter cannot be realized, it is necessary to use the approximation for ideal frequency responses. This paper deals with several standard approximations, which are the Butterworth filter, Chebyshev filter type 1, Chebyshev filter type 2, and the elliptic filter. In the following slides, we will show in much more detail each standard approximation and its dependence on the so-called filter order. First, we take a look at the Butterworth filter. The figure shows the frequency response of the Butterworth filter approximation for several different orders. As seen on the picture, the visualization was made for orders 2, 4, 8, 16, and 29. Its function is also often referred to as maximally flat, no ripples response, because the passband is designed to have a frequency response, which is as flat as mathematically possible from 0 Hz until the cutoff frequency at -3 decibels. Cutoff frequency in our case is at 2 GHz. Higher frequency beyond the cutoff point rolls off down to 0 in the stopband at the 20 decibel per decade. Then, for a filter that has an nth number order, it will have a subsequent roll-off rate of 20 times n decibels per decade. So, a first order filter has a roll-off rate of 20 decibels per decade, a second order filter has a roll-off rate of 40 decibels per decade, and so on and so forth. Also, it can be noticed that increasing the order of the filter causes a steeper and narrower transition band. However, one main disadvantage of the Butterworth filter is that it achieves this passband flatness at the expense of a wide transition band as the filter changes from the passband to the stopband. The second filter we're going to take a look at is the Chebyshev type 1 filter. The figure on the slide shows the response frequency of the Chebyshev filter type 1 approximation for several different orders. Again, we chose the same orders for the picture, order number 2, 4, 8, 16, and 29. Chebyshev filters have a significantly smaller transition band as opposed to the Butterworth filter of the same order, like we just had a chance to look at the slide before this one. But the consequence is signal ripple in the passband, as you can see on the slide. It should be noted that increasing the order of the filter decreases the width of the transition band, but then a signal with a higher number of ripples in the passband occurs. The number of ripples in the passband determines the filter order. For the Chebyshev type 1 filter, the amplitude characteristic varies between two tolerance limits, i.e., the error oscillates with an equal peak over the amplitude response in the passband. The cutoff frequency remains the same with the Butterworth filter, 2 GHz. The third filter we're going to take a look at is the Chebyshev type 2 filter. The figure on the slide shows the frequency response of the Chebyshev filter type 2 approximation for several different orders. In the passband, the filter corresponds to the Butterworth filter, but the transition band has the same as the Chebyshev filter type 1. Therefore, it is also called the inverse Chebyshev filter. These filters are almost the same as the Chebyshev type 1 filters, but the difference is that they have a maximally flat passband, while their signal ripple occurs in the stopband. For them, it is necessary to determine how much an attenuation is desired in the stopband. It should be noted that increasing the order of the filter decreases the width of the transition band, but then a signal with a higher number of ripples in the passband occurs. The number of ripples in the stopband determines the filter order. The fourth and last type of filter we're going to take a look at is the elliptic filter. The figure on the slide, as per usual, shows the frequency response of the elliptic filter approximation for several different orders. They have a sharp transition at the boundary between the passband and the transition band, but they also have a sharp transition at the boundary between the stop band and the transition band. It can be observed that increasing the order of the filter causes a ripple in the passband and stop band. It's for this reason that elliptical filters are applied in applications that require the narrow transition band, while at the same time signal ripple is not essential. We can say that these filters are optimal, which means that there is no other filter of the same order that would give the same or narrower transition band between the passband and the stop band for the same specifications in the passband and the stop band themselves. To specify the minimum order filter, we use the tool Filter Builder in a program Matlab. The first step was to set the passband frequency to 2205 Hz and stop band frequencies to 6615 Hz. After that, we had to adjust passband ripple to 1 dB and stop band attenuation to 60 dB. Knowing all four parameters, the program can easily calculate the appropriate filter order n for a particular approximation and the appropriate cutoff frequency that will mark Fc. You can see two equations that help us calculate the minimum orders of two different types of filters. They're simple fractions that have some logarithmic functions. So the conclusion was a 7th order filter is necessary to meet the specifications with the Butterworth design. And for the Chebyshev type 1 and Chebyshev type 2, they require a 5th order filter. And finally, for an elliptic filter, it requires a 4th order design. This check can be performed by including the given parameters in these appropriate equations. In conclusion, when considering design of an IIR low-pass filter, we have to consider the filter order, passband, and the stop band ripple. The reason for that is that the waveform will be misshaped if the filter response has ripples. The amount of that distortion depends on the amount of ripple in the frequency response. The Butterworth filter was found to be the best compromise, considering only attenuation of the signal. It has no ripple in the passband or the stop band. However, this characteristic is usually used only when the filtering requirement is not demanding. Otherwise, it's not effective, and it's a high price to pay for the relatively poor performance. The choice for the best approximation is depending on what signal characteristics are important. If an application requires low component count, but where neither passband ripple nor group delay is important, the Chebyshev type 1 or 2 or elliptic filters prove to be a better choice than the Butterworth one. For us, the authors working on the topic of this paper is very instructional on simulating these filters with Matlab, using Matlab, and there is a lot of there are a lot of possibilities of further development and research in this field. One could test out these filters on very specific waveforms depending on their applications. We actually have a few student papers planned with this topic in mind. For more research or deeper dwellings in one of these filters or the mentioned topics, I can recommend any of the 5 papers that were mentioned in our references. Hopefully, if you found this topic interesting, you can also read these papers. And here we are at the end of the presentation. Thank you for your attention. Unfortunately, this is an online presentation and we're not seeing each other in person. But anyways, I'm here, so if anyone has any questions, I'll try to answer them to the best of my abilities.